Hey guys, welcome back. This will be our last video reviewing the material from Statistics 1. So we are going to continue our talk about normal distribution. Again, a normal distribution has that bell-shaped curve and is symmetrical, with the middle of it being the mean, half the data values being above and half being below. So say we want to calculate the probability from a normal curve. So say we have data from an airport wait time, and it is normally distributed. And we were asked to find the probability of randomly selecting a passenger with a wait time of y minutes. So right in the middle will be our mean, and say we want to know how many people waited at least this many minutes. So the area, or the probability, would be this red shaded region. But how would we calculate that? It would be pretty difficult to do. So that's why we need to use what's called a standard normal distribution. A standard normal distribution is a normal distribution with the parameter of mu is 0 and sigma is 1. So instead of it having the mean right in the middle and then over here being the mean plus 1 standard deviation, the mean plus 2 standard deviations, the mean plus 3 standard deviations, and then to the left it being the mean minus 1 standard deviation, the mean minus 2 standard deviations, and so on. Now we have the middle is 0, and then here are the z-scores. So 1 standard deviation away, or 2 for 2 standard deviations away, or 3. And then same with the left, -1, -2, -3. Now the area under the curve is still going to be the same. The shape is still the same. But now we can take any normal distribution, standardize it, and now they can all look the same so we can analyze it. It's our way of comparing apples to apples and not apples to oranges. So to convert it, again, you have your non-standard normal distribution with your mean being in the middle and then your x values being right here. Now we're making that the middle being a 0. And then along the x-axis now is your z-scores. So recall that a z-score is the number of standard deviations a value is away from the mean. A negative z-score is to the left, and a positive z-score is to the right. So there are 3 types of probability problems that you might be asked. And we're going to go through all 3. So when asked to find the probability of a normal distribution, it will be one of these 3 conditions. Either your z-score is going to be less than the number that you're interested in which case you'd be looking at all values to the left of a z-value. So we want to know what is less than this z right here. Okay, it's going to be everything to the left. Or it can be to the left of the curve. So we want to know what is everything up to and including this z-score. It'll be that yellowish shaded region. You might be asked, okay, I want to know what is everything to the right of a z-value. If it's to the right of the z-value, it's going to be this area right here, to the right of it. Or it could be in between 2 numbers, in which case it would be the upper value from here all the way to here minus the lower value from here to here to give you the resulting middle value. And we're going to do an example for all 3 of these types. I really think that might reinforce this concept. It's a little hard to explain without having an example on hand. So some things to note is when z equals 0 will be the mean, right and exactly in the middle, or 50%. The bottom x% would be a probability, or area below the curve. So a bottom value of 5% would correspond to 0.05. The top will be the probability. 1 minus x% will be 85. And then pxx would correspond to the x percentage. So example, p of 25 would correspond to the value at 25%. So there are 3 ways that I'm going to talk about how to actually calculate a probability using a z-score. The first is the one that I think you should absolutely need to know, and that is using Table A2 from the textbook. So Table A2 is designed only for the standard normal distribution. It's on 2 pages, with the left page being for negative z-scores and the right page being for positive z-scores. So if you have a negative z-score right here, the area under the graph is going to be the shaded region. So remember, it's telling you the cumulative area from the left. So you're starting at 0, and then you're going up to that z-score. So if you're going from 0 to a negative z-score, it's going to be a probability under 50%. And then if it's a positive z-score, it's going to, same thing, start from 0, and then go all the way up to that positive z-score, which means that it will be greater than 50%. Because right here will be 50%, we're positive z-score, so it's going to be somewhat greater than 50%. So how do we use that table? Okay, so z values are found on the outside table, and just add the numbers together. So say you had negative 3.35. So you look at negative 3.35. Negative 3.35 would correspond to 0.0004. Negative 2.69 would be negative 2.6, and then 0.09. Negative 2.69 would be 0.0036. Another example was look for the z-score for negative 2.69. I think that was the one we just did. Okay, perfect. You can also use your calculator to find the z-scores. I included links for some videos. I think it does a good job of just walking you through it. And you can also use StatCrunch as well. And I provided plenty of YouTube video links for you to do that as well. Let's go through several examples. Examples are really going to help you learn this concept. So a bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So these meet the requirements of a standard normal distribution. Okay, the graph of the bone density test is as shown in the figure. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score less than 1.27. Okay, so if our middle number right here, our mean is 0. Our z-score is 1.27. We know that this is a positive number. We are to the right. And we are interested in figuring out what is the probability that this person has a bone density that is less than that value. Well, if it's going to be less than, it's going to be this value or smaller. So you start at 0 and you go all the way up to 1.27. And you're interested in getting the area of this green shaded region. So we have to look at your table right here. And if you look at table A2 with 1.2 on the left and 0.07 on the right and look at where they connect, you will get your probability of 0.8980. 1.2 on the left, 0.07 on the right, 0.8980. Okay, so that will be your probability or the area at that point. Now, this was finding the area to, the previous example was finding the area to the left of the z. Now we're going to do a example where we're getting the area to the right of a value. So same bone density test. Now we want to find the probability that a randomly selected person has a result above -1. Okay, so now remember, the middle was a 0 right here. Now we're at -1. Negative tells me I'm to the left. And I want to know what values are above this. So I don't want what's below it. I want what's above it. But here's what's important. The table is going to tell you what's below it. So the table is going to give you the area of this white shaded region. I don't want the area of the white shaded region. I want the area of the green shaded region. So all you have to do is get the area of the white shaded region and then do 1 minus that value. And then that will give you the area to the right of your z-score. So we look at our table for -1. -1 tells me 0.1587. and I want to get the area to the right of that, so I'm going to do 1 minus 0.1587 for my final answer of 0.8413. Finally, we are now going to do the area between two values. So now we want to know what probability that a randomly selected person has a reading between -1 and -2.5. So -1 and -2.5, you can't just do it straight with a straight calculation. You have to do the area of this green right here, then the area of this green right here, and then subtract the two. So that little tail right here is going to be going away. So what you're left with is the area between the -2.5 and the -1. So looking at -1, we just got that before, 0.1587. That's this region right here. Area to the left of -2.5 is going to be the 0.0062. And the difference between that area is going to be 0.1525, or this value minus that value. Okay, let's look at another example. What proportion of men are taller than 72-inch height requirement for shower heads? So heights of men are normally distributed with a mean of 68.6 inches and a standard deviation of 2.8. Find the percentage of men who are taller than a shower head at 72 inches. Okay, so we have our normal distribution. Our mean is right in the middle, 68.6, and standard deviation is 2.8. And we want to know what percentage of men are taller than 72 inches. So I want to know, what is this region right here? Okay, first things first, you have to make this a standard normal distribution. So we're going to make that mean back to 0, and then we're going to get the z-score of this 72 inches right here. So 72 minus 68.6 divided by 2.8 gives me 1.21. Now I can get the probability using that 1.21. Again, when you look at the z-score for 1.21, it's not going to give you that green shaded region. It's going to give you to the left of that green shaded region. So what do you have to do? You're going to have to figure out 1 minus that value. So 1 minus that value, so the white shaded region is 0.8869. The white shaded region is 0.8869, which would make the green shaded region 1 minus that, or 0.1123. So about 11% of men will find the design unsuitable. I, unfortunately, am not one of that 11%. Last example. When designing equipment, one common criterion is to use a design that accommodates 95% of the population. Sorry, other 5%. We have seen that only 46% of women satisfy the height requirements for U.S. Air Force pilots. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? That is, find the 95th percentile of heights in women. All right, this problem sounds complicated, but it's really not that big. So let's look at some other givens. Assume that the heights of women are normally distributed with a mean of 63.7 and a standard deviation of 2.9 inches. In addition to the maximum allowable height, should there also be a minimum height required? Height, y. Okay. So again, the problem is asking maximum acceptable height of a woman if the requirements were changed to allow the shortest 95%. Okay. So the figure shows the normal distribution with the height of x that we want to identify. The shaded area represents the shortest 95% of women. So that would make this area right here 5% and the green 0.95. So now we're kind of reverse engineering it. You're looking not at a z-score and then figuring out the probability is. Now you are starting at a probability, and now you are trying to figure out what the associated z-score is. So when you reverse engineer it, boom, you get a z-score of 1.645. With that z-score, now we can get that missing x value. This is showing you how you can do it with technology. You can do it with Excel or StatCrunch. We're going to talk about how to do it with the table. So a z-score of 0.95, the corresponding z-score to an area of 0.95 is 1.645. And then now reversing the formula, we have z equals x minus mu over sigma. So that z-score is 1.645. We're looking for the corresponding height. Our average is 63.7, and our standard deviation is 2.9. So now the resulting height would be 68.47. So that would be the height requirement. All right, hopefully you guys got that. I know that last video could be a little bit of a more complicated topic, but it's important you know it. So if you have any questions, please shoot me an email, even if it's like, hey, what are you talking about on slide 15? Thank you.